I'm going to talk a little bit about performance engineering, this process of software performance engineering, and specifically the tools I both use and develop in the performance engineering process. I work for a company called ParaTools. ParaTools is a worldwide company if you consider the world to be the United States and France. We have offices in the US, 3, and we have 1 in Paris. And this company, essentially, what we do is we make software faster. We accelerate your software. And we've been able to make contributions to national security, manufacturing, and engineering research, so we can help people get their products, out to market quicker, improve the quality of their product. And we've been able to even give tools to policymakers. The Swiss national government uses our tools in determining national air quality forecasts. Various environmental labs throughout the United States use our tools as well. And what we do and what we offer is this process called performance engineering, and that's hopefully what I'm going to acquaint you with here. The idea is that if you can lower the time to solution in your scientific code, your HPC code, whatever it may be, on any platform, you're going to lower your operating costs, right? You're going to get more science for your power. That's a good thing. You can be the first to discovery by reducing your runtime. You'll get the answer first. You can publish first. It's pretty straightforward. And the thing I think is most important is you can actually improve the capability of your HPC experiments by reducing your runtime, right? If you can reduce the amount of communication, memory, or time that your code requires, then you can ask more interesting questions that couldn't be addressed before. So lowering the time to solution by using a performance analysis tool like Tau or HPC Toolkit or Scorpy or Scholastica or NVIDIA tool, vTune, or all these tools do essentially the same thing. Make your code go faster. I'm going to talk about one in particular. I'm going to talk about the Tau performance system. I spend most of my time there. I'm going to give a few case studies of where Tau has been applied to real-world applications on supercomputers, although it's certainly been used in smaller scale systems as well. And then I'm going to end by talking a little bit about an upcoming thing from ParaTools called Tau Commander that addresses some of the usability issues and tries to bring Tau sort of to the masses. I think this is pretty obvious. In the high-performance computing world, the metrics we care about are performance, efficiency, and productivity. If we're not getting these 3 things, then we may as well go home, because that's why we're using these supercomputers, right? The supercomputers are difficult to use. We put a lot of effort and time and money into them because we need these 3 things. For the first 2, for performance and efficiency, a great way to improve the performance and efficiency of your code is to use the Tau performance system. And this is an integrated toolkit for performance problem solving. So it includes a great many different tools and commands for profile and trace generation and analysis, statistical analysis. And all these tools work together. They're semi-integrated, I would say. And you can move data between the tools. The entire toolkit is free, open source, under a BSD license. It's in use at labs all over the world. It's in use at all the DOE labs, and it's in use at a lot of corporations as well. So it's found in industry and academia. And it's not actually developed by ParaTools. It is actually developed by University of Oregon. ParaTools, because we offer a performance engineering service, I use this toolkit on a daily basis to write CFD codes, to write kinetic codes, to improve the performance of my clients' codes. But in the process of using the tool, I also add new features to it, and I fix bugs that I find. So I'm both a Tau user and a Tau developer. So I have no problem advocating the use of this tool. I'm not trying to sell it to you as a salesman. I'm actually coming to you as a user of this to say that this is a good way to improve the performance and the efficiency of your codes. Now, for productivity, Tau, I'm actually curious. So who has heard of Tau before this talk? Awesome, everybody. Well, nearly everybody. Who has used Tau? Okay, fewer people, but still a few. And who here feels like the first time they picked up Tau, they knew exactly what to do with it? Not a single. Oh, there's one. This guy knows what to do. You, sir, are a genius, because most people, when they are first confronted with Tau, Tau has so many options and so many capabilities in this thing that it's a bit like looking into the cockpit of the space shuttle. It's this bewildering mass of switches and dials and knobs. And to the expert user, to your astronaut, this makes perfect sense, right? And once you've used Tau for a while and gotten used to it, it's no problem. But initially, it's a bit of a shock. So we're working on a project. This is a ParaTools project called Tau Commander, and it is an intuitive user interface and sort of workflow environment for performance engineering in general that I'll be presenting at the end of this talk. So let me start with the Tau performance system, and hopefully I'll explain this well enough that it doesn't quite look like the space shuttle cockpit when I'm done with it. So as I said, this is a comprehensive profiling and tracing toolkit. It involves multiple tools, and it's been developed for over 20 years now. It's found at a great many institutes and laboratories worldwide. And it also works really well, not only as a toolkit on its own right, but as it is a component of a larger framework for performance regression testing, and so automated workflows as well can use different components of Tau to measure performance of your code as it's developed, and then over time to make sure, for example, you could do a nightly performance regression testing with Tau to guarantee that your performance is not degraded with the latest commit. It supports all HPC platforms. I would say it even supports all HPC platforms by definition, because we work very closely with HPC vendors, with the users, with the clients in this space, so that as soon as a new HPC system is deployed, we can bring Tau to that system and make sure it's available to the users there. It also works on a lot of systems that are not so HPC. So there's no such thing as a HPC Windows, but Tau works on Windows. If you are using Windows and you want to use like Microsoft MPI, that is supported. It also works on ARM. I've run Tau on my Android phone. And it even works in really strange environments like embedded computers. I've done Tau on the computer in my car, just for the hell of it. Sorry?
Is it a Chrysler?
It's a Toyota.
Does it go faster now?
The question was, does it go faster now? OK. So in general, Tau, or all performance toolkits either generate profiles or traces. Now, the critical difference between these is that profiles don't contain timeline data. They show how much time was spent in each routine as an aggregate. Whereas traces, every time an event occurs, we record the timestamp of that event along with the event data. And so usually profiles are enough. I find that I rarely need traces. I can usually extract information about performance hotspots very easily with profiles. But sometimes you want to see, actually see in your sort of collective operations, for example, would be a good reason to use traces. If you think there's one guy who's sort of holding up the group, you might want to generate a trace so that you can see the timestamp that everybody reaches the same collective barrier. Within profiles, there are different grades of profiles. You can have flat profiles, which just show the time spent in every code region. You can have a call path profile, which gives you everything a flat profile gives you, but in addition to the single aggregate metric for each routine, you also get a metric for each, or I should say a performance event for each call path. So if I have a function that's called from 2 different call paths, then I'm actually going to have 3 events in my profile, one for the function itself, and then one for each call path that led to that function. So this is a good way to see what routines are causing this function to take a long time. Maybe the parameters you pass to that function have something to do with how much time it spends, for example. And then sort of an extension on call path profiles is this idea of phase profiles. In Tau, you can declare phases, logical phases in your application. I can say that this is my initialization phase, this is my grid optimization phase, this is my time step phase, and this is my finalization phase. And then if I call the same function in each of those phases, I'm going to get a different timer in my profile for the same function by phase. So a good example of this would be if you have a file writing like a function, and you want to see, is it more expensive to write the initialization files, or is it more expensive to write checkpointing files in my time step loop? You would look at the counters based on phase. Now, because we have different kinds of profiles and we have different kinds of traces, you might say, well, what's best? It really depends on the kind of question you're trying to address. If you use the default settings in Tau for profiles, you're going to get a flat profile. This is red bit down here. And it's going to be a few kilobytes in size. I have never seen a profile get larger than a gigabyte out of Tau. Even on 500,000 cores, the profiles remain on the order of megabytes, barely gigabyte. However, if you turn on tracing, the default options for tracing, I think in just about any tool, will easily run into the terabytes of data. I've seen 10 terabyte traces come out of a 2K core run running for about 30 seconds. So you really have to pay attention. Don't just say, "Oh, I want traces." Just think about it, and pick the one that will answer the question that you need to address. Tau supports both direct measurement with probes that we insert into the source code and sampling, just as in HPC Toolkit. So with probes, we actually put calls into your source code that trigger Tau functions like this Tau start and Tau stop. And this gives you an exact fine-grained control over what to measure in your code. If I'm only interested in one file, and even in certain loops of one file, I can measure exactly that part and let the rest of it all just be ignored. This can be done automatically. I'll show you how that goes. So if you have a really giant code, you don't have to worry about inserting all these hooks yourself. And then with sampling, of course, there's no code modification, and there's minimal effort to get your profiles. You just use the code you have and periodically sample the the program counter, and use the debug information found in that executable to resolve those program counter addresses back to source code locations. Now you can actually do both. In Tau, you could simultaneously have probes and samples. And this is a good way to avoid blind spots in your code. If you have a piece of code that for some reason you can't insert the hooks there, then you can use sampling on that part, and then everywhere else use the direct measurement with the probes. Now I said we can insert these probes automatically. The easiest way to do that is use the Tau compiler wrapper scripts. So Tau comes with these scripts where if I want to insert probes automatically in every compiled file, I change my compiler command to be the Tau compiler command. So I would just replace whatever my MPI, CXX here with Tau cxx.sh. And there's a one-to-one match for every compiler, and Tau provides a compiler wrapper script for them all. It also supports UPC, OpenSHMEM, some of the more exotic or up-and-coming compilers that are out there. We have wrappers for them as well. Tau follows a three-stage performance engineering workflow. So when you use Tau and you're going to go and address the hotspots in your code, you begin with an instrumentation phase. Instrumentation just means adding the probes to your code. And this can be parsing the source code, add them automatically. It can be doing it yourself. It could be writing a thing called a Tau select file, which guides the source code instrumenter. And we can cover that in the hands-on. It's a little bit too much to go over in the time I have here. Tau has a library wrapping feature. If you don't have the source code to a third-party library, say you're using the system's installation of HDF5, and you want to measure the amount of time spent in every HDF5 routine, Tau can generate a wrapper around that system installation of HDF5 so that every time you call to it, the call will be intercepted and recorded along with how much data is going through, what are the parameters to the call, anything you might find interesting, you can indicate that when you generate the wrapper. We're also working on binary rewriting techniques. This is really an interesting way to do performance engineering and performance analysis. It's kind of the way of the future if we could ever get it working. Now, once you have your instrumented executable, you need to gather the data. This is the measurement phase. So typically, you just run your code, run it normally. You don't have to pass any special flags or anything to your code because it's already been instrumented. We've already added the Tau to the binary itself. If you're using sampling, you'll set some environment variables to enable that. This is the part where we would interface with external packages like PAPI. This is or RAPL. We can gather hardware performance counter data and also power data in Tau and bring those into your profile. And then finally, once you have the data, you have to analyze it. You have to extract actionable information so that you can go forward and fix these problems. And this means visualizing the data, mining the data, applying statistical methods to try to find correlations between events. And Tau comes with several tools that will help you do this. I'm going to spend most of my talk showing you screenshots from those tools, so I'll come back to that. Actually using Tau. If you want to use Tau on Mira, all you have to do really is you have to pick a Tau configuration that's already installed at this location. And there's some reference slides in the back of the slides that are online as well that'll describe this in detail. But every Tau configuration is identified by a unique make file. So whatever set of compilers you're using or MPI libraries that you're using, there's a tau makefile to match that combination. And then you find the makefile with the tags that match the features that you want to profile. So in this example with the red, I'm on a blue gene, so I'm going to use high-performance blue gene queue timers. I want to use PAPI hardware performance counters with MPI, and PDT means I'm going to use the automatic source-based or source code instrumentation. And you can see we have options in here for using ScoreP. That's a good one if you're going to use the Vampire trace visualizer, which I highly recommend. There's also OpenMP configurations if your code uses OpenMP or OpenMP and MPI together. That's all supported. Once you've selected your tau makefile, replace the compiler commands with the tau compiler wrapper scripts and rebuild your code. Then finally, execute your code as normal and get the data. So this slide here was pretty much your whole outline for using tau on Mira. Follow these directions and you'll probably get a profile. And in fact, I'll be around for the hands-on this evening and I'll be happy to help you through with that. So I'm going to spend the rest of my time here talking about the analysis tools and showing you how you use these once you have the data. The easiest thing to look at is how much time was spent in each code region. At the bottom of every slide, I'm going to have the command that I used to visualize the data, and I'm going to say, how do you get this chart? So if this chart, you would open ParaProf and click on a label in the view you'll see there. There's like a bar chart with labels for every node and for mean and for total. Just click on one of those labels and you'll get this bar chart. In this application, we can see that we're doing a lot of time in MPI all-to-all. Also, this FFT routine is taking up a lot of time. It's the third most expensive. If I change my metric to look at floating point operations, or floating point instructions, I should be careful, then I can see that my FFT routine is very computationally intense, right? There's a lot of floating point instructions happening in the FFT, which is exactly what you'd expect. And you'll notice MPI is not on this list at all. And again, this is what you expect, right? If there's a lot of floating point operations going on in your MPI, you're going to wonder, what is that thing doing, right? It shouldn't be doing a lot of math. However, if you look at data cache misses, this is level 1 data cache miss data. Okay, I see my FFT is still, has the highest number of data cache misses, so that might be a clue that I should go and look at how it's implemented. Maybe in this routine, they're striding row-wise when they should go column-wise or something like that, because this seems like a large number of data cache misses for this particular routine. MPI all-to-all is now my second most data cache miss, is the second most in this list. And that makes sense if you think about it. This is a routine moving a lot of data around, so I probably shouldn't panic just because there's a lot of data cache misses in all-to-all. Tau will show you how much memory the code uses. It'll show you a high watermark for exactly how much memory, what was the highest amount of memory allocated in your code. It'll show you total allocated and deallocated over the lifetime of your code. And it can show you in a call tree exactly where that memory was allocated and deallocated. This call tree spans language barriers. So if I have a high-level Python script calling C++ Swig generated C++ that calls Fortran, I can see all through that call stack where the memory is being allocated and being used. Let's keep going. We also track file I/O. So we can see what is the write bandwidth per file, how many bytes are written to each file. This is very useful with HPC systems, as you'll see in a minute. And of course, we also support parallel I/O. We have wrappers for the MPI I/O. So you can see bytes written in total. You can also see by MPI rank, each rank's participation in the I/O operations. Collectives, again, very important in HPC. We can see message size for every rank. We can see averages and totals. And then time spent in collectives. So if you see that your time in collective is growing as you increase the number of ranks, it probably shows there's a scalability bottleneck and that your global communication is killing your scalability. And Tau, now this is actually a very cool tool. I use this all the time. This is a 3D profile visualizer in Tau that shows you on one axis, it shows you the MPI ranks and threads in your code versus the code routine. And then the height metric here and the height and the color metrics are configurable. What I'm showing is just exclusive time. And what's great about this is it shows you patterns and relationships in your code. So right away I can see that there's this inverse relationship between these two routines. And also there's a strange sort of this double hump pattern here that exactly matches the number of cores I have per node. So there's a lot of things you can infer by looking at these patterns, especially if you start to see a sort of linear pattern, a direct inverse correlation between two routines. That probably means there's an early sender, late receiver type pattern in your communication. And I don't need a trace to see that. I can just see that by looking at the data in this view here. If you want to see more exactly who is communicating, you can take a look at the 3D communication visualizer. This shows rank versus rank. So in this case, we have everybody talking to themselves, which is not a good thing. You shouldn't be talking to yourself. So this is an artificial example. And normally you want to see something that looks a little bit like the sparsity structure of your CFD application, if that's what you're doing, right? You see something that mimics the data layout or the data communication that you'd expect. And if it doesn't look like that, then there's probably an issue somewhere in the way you're laying your data out. It's also useful to look at the actual physical topology of the data. Now, if you're running on a Blue Gene, then we have a topology file you can load that will map your profiles so that you see per rack, per physical node, who is busy. And this is a great way, if you notice in your profile that every time anybody gets on rack 5, they just are slow, that might be a hardware issue. And then you can tell somebody, hey, look, every time I go here, it gets really slow. And we actually found an issue at a Cray supercomputer where there was a chip with a bent pin. I have a picture of it, but I don't have it here. There's one bent pin on the CPU, and we found that because every time anybody ran there, it just took forever. And you can see it very nicely in the topology view. All of these pictures I've shown you are for one profile. And when I say profile, that profile contains data from all the ranks and threads in your application, but it is for one execution. If you want to do a scaling study, then you run your code for different core counts, and you can aggregate this data using a tool called Perf Explorer. Perf Explorer will give you a thing like this runtime breakdown chart, where I can see as the number of processes increase, in this case, my MPI wait all time is increasing, is becoming a more significant percentage of my total runtime. And this is due to the time I'm spending in writing this save file. So this led to finding a scalability bottleneck in S3D on Jaguar. We get up to about 12,000 cores, and the time spent in I/O is starting to outweigh the time doing useful work. Go ahead and skip over that. The other thing you can do is a event correlation. So you can correlate events with runtime. And this is a great way to see if there are patterns in sort of the underlying systems that manifest themselves in ways outside of your code, right? So in this case, the blue line is a transpose routine in a 2D FFT application, and for certain core counts, it was performing very poorly. Well, it wasn't immediately obvious to us in the way it was implemented why that would be, but when we look at this, we see that the same trend is reflected in these two routines down here. The y-axis is a log scale, so when I looked at the normal flat profile, I never even noticed that these routines were significant or had a similar pattern, but when I start to look across core counts and do this correlation, I can see that there's this relationship. And this led us to discover that there was an issue in the underlying OpenSHMEM runtime that for certain core counts would cause routines of a certain nature to perform poorly. And we were able to address that. And this had nothing to do with our application. It had everything to do with the code, the system we were running on. Now, finally, we do have a trace visualizer that ships with Tau. I recommend, if you're going to view traces, do use Vampire. It's much better than what we have, which is JumpShot. JumpShot is fine for small core counts. If you want to go up to 512 cores, maybe, then JumpShot is OK. But if you're getting any more than that, then use a big boys analyzer and go get Vampire, because it's definitely the one you want. If you want to generate traces, use tau trace equals 1 right before you run. You can have profiles and traces at the same time. Everything I've shown you here, you can turn on, right? You can turn on all the options at once if you want. You can have profiles and traces. You can have sampling and direct measurement and all at the same time without issue. It just depends on what kind of data you need. And then finally, because we have this instrumentation all up and down the call stack, Tau makes a pretty good debugger. Now, it's not like one of the quality debuggers you get from a linear or rogue wave. You can't pause your execution and look at the contents of a variable. But Tau works as a post-mortem debugger, where imagine you have a code that runs for 3 months, and only after running for 3 months does it crash. It's really hard to debug that, right? So what you can do with Tau is you set this environment variable, Tau track signals equals 1. And this makes it so if Tau detects a seg fault, a bus error, a floating point exception, any of these typical signals, it causes every rank of your application to dump out its performance data up to that point, along with a backtrace that goes across language barriers. So in this backtrace, which I apologize is completely unreadable, this is actually a Python code calling C++ calling Fortran, and I can see that all the way through. So you can easily imagine a situation where you have a very slow memory leak that takes a very long time to manifest, and finally it crashes because you run out of memory. In your profile, you'll see your memory just growing and growing and growing and growing, and it'll be immediately obvious when you look at the memory allocation call graph. What routine is leaking memory? In fact, Tau has a special flag for detecting memory leaks to address that kind of situation because it's more common than we'd like to admit. Tau includes the source code browser. So in this backtrace, you can right-click on Show Source Code, and it'll take you to the line of the source code where the crash was observed. So my math is not very good. All right, so I want to talk a little bit about a couple of case studies. The first thing I want to show you is this is a code that ParaTools is helping to optimize. This is an interesting way for doing aircraft simulation. If you have this aircraft, you can imagine you have lots of little strands floating off the end of it, and then how those strands move, affects you can measure certain properties of the flow using these strands. And what we're trying to do is implement this on a variety of different computers. It's going to be on Cray when it's available. Right now we're using Babbage, the prototype system. It's also on several iDataplex and XC30 systems. And we received this code because a client came to us and they could get up to maybe 64 cores, and then it was just not scaling anymore. So they wanted to know why. So I took the code, I did the source-based instrumentation, put my hooks in there, ran the code. This is on Babbage, and I ran this at 512 cores. And at that scale, it was immediately obvious that there's a huge problem in the way they're doing their communication. They have these barriers and these sends, and there's this nice inverse relationship between the two. Also, file I/O is fairly expensive. This little middle ridge there, that's the useful work. So the rest of this is all overhead, right? They're spending all their time moving data and talking and writing files instead of actually doing useful work. So we look at this and we realize that these calls are blocking MPI calls, right? There's no overlap of communication and computation in their code. So we developed a different communication substrate that replaced these blocking communication calls with non-blocking MPI ISEND calls. And the results were really encouraging. We now have, this is the useful work function, and we have an MPI wait all that's about the same cost as the useful work, but it's, the whole runtime has been significantly improved. We also took a look at their file I/O. The way they were writing files was a little inefficient, so we were able to optimize that. And now the file I/O is greatly improved as well. The net effect was that we were able to take this code and by looking at it in the 3D viewer, identify these hotspots, address the hotspots, and it was about twice as fast on these supercomputers. Also more scalable, right? So we addressed the scalability bottleneck, and at 512 cores, it was twice as fast. So we said, that's great, let's run at 2K cores on a Cray XC30. And this was a surprise. We ran the baseline code so we know we were starting. Then we ran our optimized code, and whoa, it was slower. What happened? I guess I broke it. So I can, try to figure out. I could try to guess a few things and see, why is this happening? But it's much easier, since I already have instrumented the code, to just go look at the profile. So I look at the profile, and it's obvious that the way I tuned the I/O for the iDataplex doesn't translate to the I/O on the Cray, right? Very different I/O systems. And so the time I was spending in this right plot 3D data had doubled. So instead of those I/O optimizations that I'd made that were great for IBM were not so great for Cray. So all I had to do was change my parameters again, and I now have optimized I/O for the Cray, and I'm back down to my approximately twice as fast. And it's very rapid turnaround on this because I already have the instrumentation in place. So I was able to take a code, fix its scalability problems, improve its runtime, and then move it to several supercomputers, just being guided by the profiles. Another example is one that happened here at Argonne. This is the IRMHD code, and it made the cover of HPC Source magazine because of the degree to which we were able to improve this code. Again, we looked at it in the 3D viewer, and we could see that there's this nasty relationship between MPI send and barrier, almost the same story. And by the time we were able to apply similar fixes, we were able to get the code to run 7 times faster. Then we also took the code onto Mira and ran it at 32K ranks, and we were able to get an additional 30% performance improvement on Mira by oversubscribing nodes. And that was again suggested to us by looking at the profiles after we'd done the initial port. So you can see that the value of these tools, it has a real value. You can definitely make codes faster, and you can be guided in your development cycle by the profiles you generate. So the last thing I want to show you in the 5 minutes or so that I have is this up-and-coming thing from ParaTools called Tau Commander. As I said, Tau, as obviously it's a proven tool. It's worked very well for a long time, but novices find it very difficult or frustrating to use. And a lot of places that don't have access to a supercomputing center, say your small university groups or your manufacturing companies, they simply don't have the time or the resources to learn a toolkit like Tau. They can't come to these training sessions, right? So what do? Well, we're developing a tool that gives context to the performance engineering workflow. Essentially, there's an object called a Tau project that you as a user create, and the project tells Tau what it is you're trying to do in the first place, right? You can tell Tau, I have a code that uses MPI and OpenMP. I'm going to run on a blue gene, and I want to see data gathered by sampling. And that, just telling that in the project is enough context that we can make intelligent decisions on behalf of the user and reduce the number of options that they're presented with. It's a little bit like if you wanted to get directions to your friend's house, and you ask your friend, how do I get to your house? You don't want him to say, well, walk out of your door and turn left and take 3 steps to your car, get in your car, drive down the driveway. You don't want the blow-by-blow of how to get to your friend's house. Just tell me your address, and I'll put it in GPS, and I'll go there. So this is how Tau Commander operates. Tell me what you want, and I'll give it to you, rather than telling me how you're going to get it, which is where we are with Tau today. This is based on a thing we're calling the Target Application Measurement Model for Performance Engineering. Essentially, all workflows within performance engineering can be expressed within these 3 objects. A composition of these 3 objects makes up a Tau project. And every time you run your application using this triple of objects, we get a new experiment. The graphical user interface for Tau Commander looks like this. We're borrowing a leaf from IPython and trying to organize it into sort of performance engineering notebooks. We're also looking at interfacing with Jupyter so we can actually become part of the IPython Jupyter ecosystem. And you get a nice graphical interface for organizing your projects and organizing your workflows. Again, this is all, hopefully I'll be able to give this to you in the hands-on next year. But I just want to show you this now in case there's anybody out there who wants to help me with it now. If you think this is pretty cool, I would love to work with you, and we can try it out in your codes. It's on GitHub. Tau's command line interface is significantly improved using Tau Commander. You have a help flag at every stage of your workflow, so if you ever get lost, you just say help, and Tau Commander can give you advice. There's a dashboard command that will display all your current configurations. And so you can see at a glance, your whole system configuration, what options do I have available to me? If you use Tau Commander on a system that has never been touched by anyone from University of Oregon or ParaTools, and it doesn't have the dependency Tau needs, if you try to use Tau Commander, the first time it'll go in there and see that you're missing these things, and it'll download them, configure them, install them, make sure that everything is set up. And this is working for all the platforms that Tau supports. So this takes a lot of the headache out for first-time users, especially if they're coming from the Windows land where things are just point and click. This is much simpler than trying to figure out how does configure, make, install work for 6.5 packages. And then finally, Every time you run your code under Tau Commander, it creates a new trial of an experiment. The point of this is, again, provenance, which we've heard a lot about. This records completely the parameters that generated your performance data. So if at a future date you have to defend those numbers and say, yes, it was this fast, you know exactly what system we were running on, you know all the environment variables that were set, you know all the software versions. There's MD5 checksums of all relevant binaries included in the experiment. So there's, I would say, far more data than you would need. You should be able to completely recreate these numbers, or at least explain where the numbers came from, using the experimental data from Tau Commander. If you change configurations in Tau Commander, it detects that and it will reconfigure a Tau as necessary. It can automatically reconfigure reusing previous configurations as well, so it avoids a lot of sort of this missing option problem that you sometimes find with new Tau installations. And the workflow is unchanged. If you change your configuration from serial to MPI with OpenMP, the commands you use are exactly the same. The only thing that's changed is your project file. So Tau Commander is now aware that you're doing a different task, and it can adjust accordingly. So if this is interesting to you, I encourage you to try it out on Mira or Vesta. If you have access to Argonne, to any of the other national labs, there's probably Tau there as well. Tau's at CSCS. We also have Tau Commander on GitHub. It's sort of as by invitation. I extend this invitation to you. If you are interested in trying this, please let me know. And finally, I want to mention that if you want to get started with these tools very quickly on your laptop, we have a Linux distribution available as a virtual machine that comes with Vampire, Intel compilers. I think we have a Linea DDT in there. I think we have a Rogue Tonal View in there, and of course we have Tau. If you download this installation, this VM, you can get started with these, try them out on your codes, right on your laptop. So that's a great place to start. And these are my sponsors, and I'll take any questions. Yes?
Is the VM at the last website?
Yes, yes. This is the VM here. All right, thank you. Yes?
So, for Tau Commander, if you even want to use it, how can you instrument it? I mean, normally when we use Tau, we have to instrument it, right? And recompile and stuff like that. So if you want to use it through the GUI that is shown as slide,
Right.
How can you instrument it?
So the GUI there, that's the GUI generates a project file which you deploy to the command line interface at your site, right? And that command line script will handle the instrumentation and everything for you based on the project. Yeah, you're right. The instrumentation is not done in the web browser. It's done on the command line at your site. Yes?
This can profile and give us information of Python also?
Yes, yes. So we support Python and then mixed language environments.
So our code is actually a code which loads shared objects either in C or CUDA or OpenCL, and then it runs it on the fly. So while compiling those, we should pass it as with those flags, is it? Tau CC?
So it depends on what the information you want. If you want to see information on the Python level, you don't have to do anything. Replace your Python command with tau_Python, and this will start and stop a timer every time you every time Python calls your native language object. It will record the time spent in that native language object. If you want to see time spent in each routine within that object, then you'll have to compile those objects with the Tau compiler wrapper scripts as well.
This works with CUDA as well?
This works with CUDA as well, yeah. This works with CUDA, it works with Mike. It's going to work with Knight's Landing.